Hello, everyone. Welcome back to the AAS YouTube channel. And we're back to the good stuff, which is the AAS Journal Author Series. And I'm super happy to have Nancy Evans with us today. Hi, Nancy.
Hi, Frank.
How are you doing today?
Not bad, not bad. Pretty warm in Massachusetts, but we can hardly complain, I guess, to somebody in Arizona.
Yeah, we're going to be a bit toasty today, 117, 118. But on the other hand, we don't, well, this time of year, we do have some humidity. We do get the Gulf Coast humidity rolling up, but still probably not as much as East Coast humidity, but good. So is the CFA planning on opening? Is Harvard planning on opening in the fall?
CFA is opening very, very carefully and very, very gradually. There are some people necessary who are going into labs now. Delighted, it's wonderful that the Chandra satellite is being run by now mostly remotely, and everything has really gone very well. I don't even want to think about the things that they probably had to overcome. But anyway, it's one of those real landmarks. It's great to know that they're managing as you wouldn't know it.
Yeah.
Satellites are remote anyway, so
they've already got plenty of social distancing going on and how we interact with them. So that's cool. Nancy, what do you like to do for research broadly?
Well, for a long time, I have been working on Cepheid variable stars. Interestingly, and as a matter of fact, this was my thesis many, many years ago. But there are so many things which have happened, which have posed new questions for us and also given us lots of new ways to attack them. So even though I feel like I've been doing something along these lines for a long time, there really are continually new ways new things to work with, new data to work with.
That's fantastic, right? Field keeps moving. So with that, let's go ahead and get into this lovely paper that you are headlining. And I'm going to do a complete desktop share on this one. And so we are going to cover X-ray observations of the peculiar Cepheid V473 Lyra, identify a low mass companion. And Nancy, take us away.
Okay, and I guess my first line should definitely be, you see a long author list, and everybody has made very nice contributions to this paper with some certainly somewhat complicated observational data. Anyway, most people know about Cepheids. This paper, it turned out, brought together, involves two areas of research which were brought together in a way that we really weren't expecting at the beginning, but that's research. For introductions, I'm going to actually be talking about two different topics, which will then come together in the end. So we're starting off complicated here. And this very nice figure on the left of the screen was put together by Scott Engel, who works a lot with Ed Guinan. This was an important part of Scott's thesis. And I am delighted that we can have an extra graph because I think this one really explains a lot. Do I have a cursor or something? Can you see my cursor?
You guide me, you tell me where to go.
Oh, okay. Well, the bottom three panels, the green one is the standard Cepheid light curve. The blue one underneath it is the radial velocity curve. And the red one at the bottom shows what the radius is doing. Cepheids, of course, are pulsating variable stars. There's a pulsation wave which starts down in the envelope and moves up through the atmosphere. Cepheids feature in all basic textbooks because the period with which they pulse, the pulsation period, is directly related to the luminosity, which is a wonderful way to determine the distance. And all of this has been reviewed lately in no small part because of what's called the Hubble constant tension. the Cepheids are the basis for the extragalactic distance scale. As you start with Cepheids in the Milky Way and nearby galaxies, and then you work out. And they give one answer for the Hubble constant, the expansion rate of the universe. Yep. But this is in conflict at several sigma with the expansion rate, which they're now getting from the Planck satellite. So it is well worth refreshing everything that you knew about Cepheids from from your basic textbook, because it's one of the hot topics these days, to see what that can tell us about what is going on. So
there's also some tension with the tip of the red giant branch method, right? So that one's another one. That's
right. Any way that we can link, any way that we can derive, it's a very nice term, the extragalactic distance scale ladder. You have there's these Cepheids we can do fairly nearby. When you want to move farther out, you have to move to other distance indicators, and different indicators come into play at different distances.
Yep.
So the specific Cepheid in the paper is called V473 Lyra, which is the shortest period Cepheid still, I think, in the Milky Way. Has a period, pulsates with a period of a day and a half. But let's see, can we go to figure 7?
Figure 7. Let's slide down to all good. Figure 5, figure 6, figure 7. There we go.
Especially, and it's the one at the top of figure 7. V473 Lyra is essentially unique. It may have some cousins, but it is essentially unique in the top figure shows the radial velocity amplitude of the pulsation period over time. And there is quite a dramatic change over a fairly well-established period of a couple of years. And this is just not what Cepheids do. Cepheids are usually well-behaved stars, and often they repeat in a rock-solid way. You plot a light curve from 1950 on top of a light curve from 2000, and they'll match beautifully. Not this one. So, however, it is the best explanation, or the best description is that it is indeed a classical Cepheid. The classical Cepheids are youngish. They will have masses of 4, 5, 6 solar masses. It is presumably pulsating in the second overtone.
Yeah.
This variable amplitude, which in itself is, as you can see, quite repeatable. Now, this is the kind of thing they see in RR Lyra stars called the Blaschko effect. They're kind of cousins of Cepheids, but physically quite different, lower mass, much shorter periods. So they do this. This V473 Lyra is the only Cepheid that we know that does this certainly to this kind of degree. So deciding any evidence which shows that it is in fact a classical Cepheid, which we think it is also useful in interpreting.
Let me ask a question about figure 7. What is going on the right, where you have these near vertical strips?
Oh, okay. That's just the same. That is the same thing happening. The data on the left was a long series of data from the Geneva Observatory taken by Gilbert Berkey, and then not much data. The Hungarian colleagues, who appear also as co-authors, worked hard getting some new observations much closer to the current time. So this is quite a long time span from sort of 1970 to essentially up to the present.
Got it.
Okay, now, as I said, Cepheids, I used to say they're non-destructive testing because we learn a lot from the pulsation period. The basics, the luminosity, the central luminosity from the core doesn't change. This is an envelope phenomenon.
Mhm.
And there's some things that we know quite well about the envelope phenomenon. Back to the figure on my nice explanatory figure on the left here. As you can see, if you look down at the phase of minimum radius, which is about phase 0.9, this is the phase where the pulsation wave is coming up from the envelope, moving through the atmosphere, and then it moves out through the chromosphere and presumably on up higher. And as you can see in the top two figures, there are not a bunch of things that happen. So, yeah, we know the photosphere is being perturbed. Quite a few ultraviolet lines go into emission, and you see the sharp peak there at that phase. Microturbulence jumps up. So we know the photosphere is being stirred up.
Yes.
Now, as I said, two topics to this talk, and the other one, and as I say, talking about new capabilities which we have, is what happens if you look at them with X-rays.
Yep.
And it's the third figure down that shows you what goes on there. This is from Ed Guinan and Scott Engel, and as you can see, at minimum radius, when everything is going crazy in the photosphere, the X-rays don't care. They just work along and do not very much. And Ed and Scott, bless them, I mean, that's the phase that you would pick to say, oh, I bet I'll see something at that phase. Ed and Scott, however, kept on looking, and lo and behold, if you can see at phase, it's about phase 0.5, there, and this is a phase where, well, we got some gaps in our data, but the photosphere is very normal. Nothing's going on in the photosphere. The X-rays jump up by a factor, by something like a factor of 4. This, by the way, is for the prototype Delta Cephei.
Okay.
And the two colors show two different cycles that it occurred in. So it wasn't just once, it occurs, it recurs. And so we have here an X-ray phenomenon, which is tied to the pulsation period. So it seems as though there is a connection, but we certainly haven't figured out yet exactly what that connection is. So let's see now, if we can go to figure 6, which is one page up. Which, yeah, a little, oh, good, wonderful. This kind of summarizes what we know about X-ray observations in Cepheids. It's the phase 0.4, which we found in Delta Cephei. The open sort of square and circle, those are the fluxes, the luminosity that we see. Yes, there in Delta Cephei. The line down at the bottom, this is the line with what we see at quiescent flux. So that is really applicable for 0.7, 0.8, 0.9. There is a second Cepheid, Beta Doradus, which is shown by the X, and in particular the big X. Which seems to have the same activity at the same period.
Yeah.
Now, one of the other areas that I have been working in is what are there companions of Cepheids? You can have spectroscopic binaries. In this case, we're particularly looking for something which might be a visual binary, and we're just finishing a paper on the final part of that yet. Now, if you are looking for a faintish star near the Cepheid, there you have a pretty good chance of picking up just a field star. But X-rays are a wonderful way to discriminate between a star which might be a Cepheid companion because it's young enough to be. The field stars are on average quite old. any low mass stars like Cepheids, they have a convective envelope, so they do in general make have magnetic fields which produce X-rays. But over time, and this is certainly one of the things which Kepler has shed a lot of information on. Over time, the rotation decreases and the X-rays decrease. So if I take a one solar mass star and it's as young as a Cepheid, say 50 million years, it'll have a nice X-ray flux. If it's an old field star, it's much, much lower. So we were doing a survey of our possible companions, and indeed a few of them were the little triangles are all the ones where we had upper limits, didn't see any X-rays, so we know that those are just field stars. They're not genuine companions.
Okay.
However, if you slide the pointer up above the Cepheid region, yeah, up to the lonely black dot there, V473 Lyra was one of the targets which had a possible companion. And that dot is not from the companion, but that is from something which is unresolved from the Cepheid itself. So we had another detection of a Cepheid at just the phase that matched where we had seen an X-rays in Delta Cephei.
Okay.
Of course, you never want to be, you always want to check these things out. And plus the fact that we have this funny amplitude variation for V473 Lyra meant that if we got it at a different amplitude phase, well, we might learn something about what the atmosphere was able to produce. So we applied for an X-ray observation with the XMM Newton telescope, which is run by ESA. And figure 1 shows you what we got.
Okay, figure 1.
And I think we're a bit more sensible from here on in terms of figure ordering.
All good.
This is the X-ray observation, the count rate from the XMM exposure. And as you can see, nothing, it jumps around a bit, but there certainly doesn't, the best way I would want to describe the data is I would just put a straight line through it and say, that's what we've learned.
Yeah, zero to order.
There is certainly not a burst of X-rays. And so if you go back to figure 6 again, yeah, there we go. The two black circles at the top with the bar connecting them, that's the duration of the XMM observation. And as I say, essentially what we see is a constant rate, which is very different from what the Cepheids are, from what Delta Cephei is producing. It's a real burst, a jump of a factor of 4.
Right. Okay.
So, but I think we might as well go back to figure 2 and work our way through some of the rest of the data here.
Figure 2, there you go.
Okay, this is what the X-ray spectrum from the XMM observation looks like. And it's what would be described as a fairly soft X-ray spectrum peaking at 1 kilovolt. This is not unusual. This is not unusual for a stellar spectrum. This is kind of what they look like. If you want to slide it up once more to figure 3, as I said, we have we wanted to be really careful with the phasing for this because the amplitude variation is a bit funny. So the black areas here there was some photometry done in Hungary. The gray area shows where the XMM run is. So we really have current photometry. So we really do know the phases of the XMM run in the Cepheid period. And if you think this is overkill, if you move on to the next figure, this is what phase variation looks like. As I say, this is a tricky star, but the two red points come from the photometry that we just saw above. So yeah, again, we really do know what the phase is. The gorgeous curve, figure 5, is TESS observations from the TESS satellite. Now those don't actually fold in particularly to give this information on this topic, but that certainly should whet your appetite for some of the current kind of satellite observations that we have.
Yes.
So what do we make of all this? Well, it really doesn't seem as though the X-rays cover half what would be the pulsation cycle. It really doesn't seem that we are seeing any sort of variation which is tied to the pulsation. The best answer, the best guess would be that, in fact, there is a low mass companion, young enough to be a Cepheid companion, making X-rays. The X-ray luminosity is quite consistent with what you would expect for a low mass companion. So how can we move on? What else can we say about, what else can we learn about this this potential companion? And for that, I think we're back to figure 7 again. Oops.
There we go.
There we go. Okay, the first thing, if you want to decide whether something is a spectroscopic binary, the first thing you look at, usually the first thing that alerts you to this as a possibility, is to look for radial velocity variations due to orbital motion. This is a little more complicated for Cepheids than for some stars, because if you remember the first curve, the pulsation produces radial velocity changes. So you have to correct any velocities that you have to correct that for pulsation. And of course for V473 Lyra, this is going to be doubly difficult, because not only do we have a pulsation period, but we have a variable amplitude to the pulsation period.
Mm-hmm.
So the bottom part of figure 7 is where we have made we've made the first correction for pulsation velocity, and you can see that it goes for the top figure has an amplitude of something like 20 kilometers a second. Bottom one, it's down to about plus or minus 2 kilometers a second. We're trying to see if we can see a signature of orbital motion in the velocities that we have. Now we can see from the data that from hour to hour and from night to night, there's probably more. There probably is more variation. There probably is more variation. Probably some of it is just noise. So, in order to see if we could do any better on on either orbital motion or limits to orbital motion, we did the figure, what is it, figure 8 down at the bottom. And maybe you can slide it down so we can see both 8 and the bottom part of 7. Is that?
Yep.
Yeah, that's fine. So here we bind the velocity data into bins of a year. Now this is not a silly thing to do. Orbital periods for Cepheids, which are post-red giant stars, the ones we know start at a period of a year. So we're not smoothing out something which had an orbital period of a month. That probably is not true for a Cepheid. And as you can see, the X's down at the bottom are the data binned in 1 year period. So we do have a very nice data string there, thanks to Berkey. And as you can see, instead of plus or minus 2 kilometers a second, we're down to plus or minus 2/10 of a kilometer a second. So that's a much more stringent limit. And furthermore, we did a second thing. If you look up at the top of figure 7, as we can see, there are periods where the pulsation amplitude is very low, so we'd only have a very small correction to make due to pulsation, and other periods where it's much larger. So we pulled out the data at the phases of low pulsation amplitude, and those appear as the asterisks down in figure 8.
Okay.
And they agree with the ones that we just binned for a year. So I think that's pretty good indication that we are not seeing orbital motion with any amplitudes larger than about 2/10 of a kilometer a second. So that's a nice limit that all of these data, little tricky to analyze and pull them out of, but I think that's a pretty solid limit.
Nice.
So there are, in fact, a couple of other ways which we can learn about the parameters that we have for the companion. And figure 9 shows you something which we get from Gaia data. Gaia data, of course, has proper motions, and in particular, Pierre Cavallo took a look at the proper motions in the Gaia data and in the Hipparcos data. And again, there is no indication of orbital motion that we see. So figure 8 shows you then what is permitted in terms of the mass of the secondary star, M2, and an orbital radius from the fact that we don't see any orbital motion in the Gaia data. Now, when I've been talking about a low mass companion, what we're thinking about is you could have it could be a solar mass, it could be half a solar mass. On the other hand, we are not expecting it to be anything like down at the bottom. We have, less than 1/10 of a solar mass. So what we get from the limits that we get from the Gaia data are the solid green line is the limit and the light green is the error possibilities. So if we think we are likely to have, plus, we have a good solid X-ray detection. So the star can't be too minuscule. So if we're expecting a star which is half a solar mass or a solar mass, it's got to live up in the upper half of the diagram, which means it's going to be confined to something which is, say, if you look carefully, you don't have to blow it up, but it's going to have an orbital radius of say 30 AU or more. Wider radius will have a much lower orbital radial velocity. So it could live out on the right-hand side of this diagram and still have a reasonable secondary mass of half a solar mass, something like that. So we have a limit from the Gaia data. There are some blips over here on the left. Now, if the orbit was down at this main peak here on the left, we would certainly see that in the orbital velocities, in the radial velocities. And we don't. Now, of course, it's always possible to have a pathological case where the orbit is completely face on, and then you won't see any radial velocity. But that is way down at a very low probability. So we have a limit from the Gaia data that the companion should be 30 AU or more or less. So that's already something we know about where the companion would be. And if we go to figure 10, we have another limit. This is from a Hubble Wide Field Camera 3 survey of Cepheids. On the left is the image itself. which, as you can see, has a pretty nasty point spread function. The Cepheid is, at the very least, the Cepheid is much brighter than any possible companion, and the point spread function, as I say, is pretty nasty. Moritz Gunther, who's one of the co-authors here, has done a very good job of doing point spread function correction, resulting in the figure on the right, and from which we concluded that there's nothing in the field outside something like half an arc second, which at the distance of V473 Lyra translates to 300 AU. So we have reasonable limits on we think on a companion, which we think should be between 30 and 300 AU. So as I say, this was not what we expected. We did not expect it to be a companion. It's perfectly reasonable, but it wasn't what we expected.
Right.
So we really there were really, I think, three conclusions that came out of this paper. One is that the X-rays, the Gaia, the velocities, and the Hubble are all consistent with a low mass companion, solar mass, half a solar mass, between 30 and 300 AU, a very plausible scenario. The second thing to point out, I think, is that it took X-rays to reveal this companion.
Yeah.
You can see in Figure 8, to find a companion which is 5 magnitudes fainter than the primary star. Well, in the visual, it's completely dominated. The Cepheid completely dominates the field. If the companion happens to be hot, you can look at it in the ultraviolet, and that can tell you a lot. But if you have a companion which is roughly the same color as the Cepheid, it's you can't use wavelength. You can't go from ultraviolet and the visible. That's not going to tell you much about the companion. And it is very useful. You want to have good statistics on Cepheids are reasonably intermediate mass stars, fairly massive stars. You'd like to have some good statistics on, and when you find them in binaries, are they likely to be in equal mass pairs? Are they more likely to have a lower mass companion? This is an important question for star formation.
Indeed.
And so the X-rays are extremely helpful. In fact, almost the only way of finding low mass companions, particularly for an evolved star like a Cepheid. And finally, the fact that, as I say, the most plausible explanation is that you have a low mass star and it's producing X-rays. Is another confirmation that this is, in fact, a population 1, reasonably massive classical Cepheid, as opposed to, for instance, if you had exactly this same companion, which was a companion of an Lyra star, which is much less massive and much older, the older companion would not have a nice strong X-ray flux. So yeah. This is another confirmation that this strange star is in fact a population 1 classical Cepheid.
Cool. Cool. Very nice, very nice. So there are lots of mysteries about this one. And if you look in your crystal ball, Nancy, where do we go over the next, let's say, couple of years? Where should we go?
Well, for this particular star, there's nothing at the moment which I'm thinking that is gonna help us work these things out. Okay. For Cepheids, the discovery of the X-ray pulse in at least a few classical Cepheids. You need X-rays. No stars produce a whole lot of X-rays. Cepheids aren't copious producers, so it takes a chunk of X-ray time. X-ray observations are very valuable. This is certainly one of the things that we're particularly interested in following along, getting some additional observations to see if we can broaden the sample of what we see. And one of the crucial questions that this is tied in with is the question of whether Cepheids and particularly in present, whether the pulsation causes any kind of mass loss. Because that's what you need to match them to the tracks. Okay. So, you know, if I could snap my fingers and say, what would I like the most? I think, you know, I think some more X-ray observations would be.
Well, there you go. Very cool. Very cool. Nancy, I want to thank you so much for sharing your lovely paper with us and your time with us today. So thank you.
Okay, it was fun.
All right. All right, everyone. Thank you so much. And we will see you on the next one. Bye-bye.
Bye-bye.